I'll briefly say some things about differential forms and do a quick review. So, okay. Why? So first, let's do a brief review. Hopefully, this will take maybe 20 minutes for the old thing, 5 minutes for the new thing. We'll be done. Differential. Okay. So, does anyone remember from last time what was the original quest we set on? How did we motivate all of this? Why did we want to look at these things? Yes? Why did we want to think about differential forms?
I haven't actually watched it yet.
Okay, it doesn't matter. Ask Ife. Why did we ask Ife?
I think you want to.
It was one word answer. Volume. Yes, we wanted to have some natural tool to talk about volume. And particularly, we wanted, we said, okay, if I want to talk about volume, how do we usually talk about volume? We take something, split it up into tiny cubes, and then compute the volume of the cubes, add it back up, and get the total volume. So first, let's understand the volume of a cube. Okay, this is what we wanted to do first. Or not a cube, but maybe something that's a parallelepiped. And we realized that this is precisely described by an alternating K tensor. So it is some function which takes in K vectors as input, is multilinear. So meaning that omega of v1 dot u plus vi plus lambda u dot vk is equal to omega v1 dot vi dot vk plus lambda omega v1 dot u vk. So it's just linear in each entry. Does that make sense? Takes in k vectors, is linear in each entry. Sorry, it outputs a number. R or C, I guess. Either is fine. Actually, no. We want volume to be real. Let's stick with R for now. But principle could be whatever if you generalize things. Okay, multilinear and alternating, meaning that if I swap two entries, I just pick up a minus sign. There's a minus sign. So we realized if we want to talk about the volumes of things, particularly volumes of parallelepipeds, we have to look at these kinds of objects. They take in a bunch of vectors, it's linear in each entry, and it's alternating, meaning that if I swap two things, that I just pick up a minus sign. Okay? Good. And so, for example, a K form will tell me something about K-dimensional volume. So a 1 form will tell me something about lengths of line segments. A 2 form will tell me something about areas of rectangles or parallelograms. A 3 form will tell me something about volumes of parallelepipeds, and so on. Does that make sense? Yes. So then, what we said is, okay, this is very nice. Now we want to kind of understand how these forms look like. Okay, how can we study them? And one type of forms that we understand really, really well is what kind of form? Where k is equal to what? Well, I mean, there's two that we understand really well. Well, that's very hard. That's very hard. Very hard. 0 and 1, my favorite one. So let's denote the space of forms as this omega symbol. So constant forms, okay, this is just constant numbers, okay, not very useful. Well, it is useful, but okay. We'll talk about one forms. Those tell me lengths of what? Of what? Of line segments, roughly. Yeah, so vectors. So one forms. So suppose I have a vector space V. Suppose we are on Rn. Okay, and I look at all the one forms in Rn. Okay. Okay. What is a one form in Rn? It's something that takes in how many vectors? One vector and outputs a number, and it is linear. Do you agree? So that's something we know really well. This is just the set of that's Rn dual. So that's the set of linear functionals on Rn, right? We understand these really well. And so then we came up with the notation for this thing, where we said that omega, we will write it as a1 dx1, an dxn. We choose this notation dx1 dxn, where what is dx1? Dxi is going to be something that takes in a vector, outputs a number, and it's going to do, how is it going to do this? It's just going to output the ith component of the vector. Okay. So now whenever I write dxi, I just need a linear function. So something that takes in a vector, outputs a number. Okay. Does that make sense? Does this make sense? When I write dxi, I just mean a function that takes in a vector, outputs a number according to this rule. It just gives me the ith component of the vector that I put into it. Yes? Okay, very good. And so it's what we later realized is that it turns out I can build a K-form out of one form. So this is something we realized. And how did we do this? We did this by defining, okay, I'll write it here. We did this using the exterior derivative. Oh, not derivative, exterior multiplication. Okay. How did we do this? So we defined this thing where if I have an omega, a K form and an L form, then I define the exterior multiplication of these two things, which I denote using this wedge symbol. And this is going to give me a new K plus L form. It's going to take in K plus L vectors. Let's do it. Yeah. And how do I define it in terms of the whole thing? I define it as a sum minus 1 to some sign, some permutation of omega k, v I1 v I k times omega L v J1 v JL. Okay? Where I specifically order things to be IK, J1, it's less than JL. And so this is the kind of the sign of permutation. And so essentially what I do is I take omega k, this takes in k vectors. I take omega l, it takes in l vectors. And what do? I take the inputs, I mix them up, plug them into the k form, plug them into the l form, multiply them together, and then add that up over all the possible permutations. Well, it's not quite over all the possible permutations. You could add it up over all possible permutations, but then I need to have like a normalization factor in here. That's roughly the idea. So I have these two forms, and I have k plus l vectors, and I want to do something to these two forms to get a new form which takes in k plus l vectors and is still multilinear and anti-symmetric. So how I do that is I just kind of take this form, plug in some vectors into it, take the next form, plug in the leftover vectors into it, multiply it by some sign, and add up over all of these possible ways to rearrange the vectors. And the point is that in the end, I get something that is alternating and multilinear. Okay, so now we have, using this definition, I have a way to take a k form and l form and get a k plus l form. Okay, do you agree? And so it turns out that now I can, using linear functionals, I can now build forms of any degree. I just need to wedge enough I just need to wedge enough dxi's to get a k form, k plus 1 form, whatever. Okay? And so I'll give you an example. Okay, that's good. I'll give you an example. For example, dxi wedge dxj is going to be what? Well, so I plug in two vectors into this. This is just going to be dxi of v1 times dxj of v2 minus dxi of v2 times dxj of v1. Okay? This is kind of an example. So this is just how this exterior derivative would work on two forms. I take the first one, plug in v1 into it, take the second one, plug in v2 into it, then I permute v1 and v2, right? I pick some other permutation. So I swap v1 and v2, but then that picks up a minus sign over here from the thing. And so then I have dxi, the first form, plug in v2, dxj, plug in v1. And you can check that this satisfies these conditions. It's linear in each entry and is alternating. So this is good. Okay, does this make sense? So this is very useful. Why? Because it turns out that the space of k forms on Rn is in fact spanned by kind of all the possible ways to wedge k dxi's together. So it turns out that if I look at these linear functionals and just wedge enough of them, then I can use that to kind of build up any differential, any form that I could possibly want. Okay. Now notice that you want to have all the dxi's to be distinct from each other, right? Because otherwise you get 0. dx1 wedge dx1. If I was equal to j here, I'd get 0, right? So I need to have a distinct dxi's. Right? People see, because of the alternating condition, that means that if I would like swap two vectors or something, I'd get the same thing, so I'd get 0. Okay. So this is good. So one thing, can someone tell me if k is equal to n, what is the dimension of this space? Actually, you know what? I want Alex to answer. So if k is the space of k forms on Rn is spanned by I take k dxi's and then wedge them. Okay? How many ways are there to take n dxi's when there are only n dxi's? How many ways are there to pick out n dxi's if there are only n dxi's? You can't answer. Someone else. And Miran can't answer.
I never learned this. I should be allowed to answer this.
If no, this is everyone should know this answer. If I have n balls and I want to pick n of them, how many ways are there to do that? Yes, there's one way to do that, precisely. And so this means that lambda n on omega n on Rn is in fact spanned by one thing and one thing alone, dx1 dot 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 dxn. So yes, putting them in a different order, wedging things in a different order just gives you minus signs. So wedging things in a different order is all the same. Do people know what this thing is called? You do. So what's something that tells me the some function that tells me the volume of an n-dimensional parallelepiped in an n-dimensional space? Yes. So this is precisely the determinant. The determinant is very special. Why? Because it's kind of the unique thing. This space is one-dimensional. You only have the determinant and scalar multiples of the determinant that give you n-dimensional volume in an n-dimensional space. The determinant is unique in this way. Okay. Do you agree? So from this, you kind of see. So I can look at k forms in an n-dimensional space. But what is more interesting is that if I look at an n-dimensional form in an n-dimensional space, then it tells me volume in a kind of, tells me something about volume in a unique way. And so, okay, now we have this whole discussion of volume. We can now start kind of going backwards, right? The motivation at the very beginning that I gave the motivation that, look, I want to find volumes of various shapes. And what I want to do to these shapes, I want to cut them up into little rectangles. So I have some area. I want to cut it up into little rectangles. Compute the area of the rectangles and add it back up, right? The usual thing that we do. And so I said first, before I do this whole thing, first let's deal with the volume of a single rectangle. Okay, this was us dealing with the volume of a single rectangle in an n-dimensional space. We realized that we have to kind of study these n forms on these n forms. Okay? And so now, what we would like to do is we would like to kind of consider an arbitrary blob and use forms to do whatever. So what I can do now is I can allow my forms to have coefficients which change in in space. Okay, so now omega in so a k form on some manifold M is going to be what? It's going to be something where at every so it will be something that takes in a point on the manifold and a vector and is going to output a number. Okay? So roughly what this is saying is at every point on my manifold, so whatever it is, at every point on my manifold, I'm going to have a form that is going to tell me kind of how does volume work at this point. Do you agree? So it's at every point, I'm going to have something that tells me if I plug in these tangent vectors into it, what volume do I get at this point? Why does this matter? Because in principle, I could have some like curved surface, and so as I move around on the surface at different points, kind of it gets stretched more or less, and so the volume could kind of be a little different from one point to another. Okay, and so what we will, and so what this is going to correspond to is, look, before we said that the thing is spanned by these dxi up to dxik. All this changes is that now, so every form was some linear combination of these things. Now it's going to be a linear combination where the coefficients in the linear combination could depend on where I am in my manifold. Okay? So for example, in a one-dimensional case, a one form, xb, could be, I have some xy coordinate dx1 plus b xy dx2. Okay? Right? So this means that this is a one form in the two-dimensional plane, right? So at some point xy, I have some number dx1, some number dx2, and that tells me here locally how do I measure lengths of line segments kind of locally around this point? How do I measure lengths of line segments locally around this point, and so on and so forth. I just kind of allow the lengths of line segments can be different in different points of my space. That's all this does. Okay. And now what I do, okay, it's good, is we define how to integrate these things. Right? Because I told you about volume. Now what we want to do is we want to integrate this. Well, if I gave you, so one thing that we first need to realize is that if I want to be integrating something, my dimensions have to be matching up. If I want to compute a two-dimensional volume, I have to be computing it on a two-dimensional shape. Do you agree? So we can integrate k forms on k-dimensional spaces. Okay? That's that makes sense. That's the only thing we can do. We can only integrate k-dimensional forms on k-dimensional spaces. That's good. Actually, maybe I should take the microphone. I think I'm still audible. Okay. Integrate k forms on k-dimensional spaces. And if I have a k form on a k-dimensional space, I know it has to look like what? How does a k form on a k-dimensional space have to look like? There's only one kind of distinct one, right? It's going to look like what? It's going to look like dx1 wedge dot wedge dxk, right? Okay. And the difference is now I know that in principle this could depend on k coordinates, right? This is what I said. Do you agree? Okay. But do we know how to integrate this? Do we know how to integrate this in principle? Like it looks like we know it. So we will define this for we will define. So if omega is a k form on a k-dimensional space, then we will define its integral over some region, right? So this means omega is f of x1 xk dx1 which dxk. I will define the integral of omega on whatever region to be precisely just the usual integral of this function f of x. Okay, I will define this thing to agree. In this, to just agree with what we would expect. Do you agree? Okay. But what could happen? Okay, I will now erase this part. What could happen is, this is kind of doing this in flat space. That's very easy, doing things in flat space. We know how to do that. But suppose we had our form defined on some manifold, right? How do we integrate this? Well, the whole point of a manifold is that there are what? For a manifold, there are... Yes, there's local coordinates. I can give it coordinates. So I know how to integrate a K form on a K space in RK, right? So then on a manifold, to define the integral on a manifold, I'll just define it in coordinates. So let's say phi be some coordinate chart from RK into my manifold. Then the integral over the manifold of omega will be defined as the integral over, no, I guess not RK, but U subset of RK. Will be the integral over U of the pullback of omega by phi. What does this mean? This means, so phi star of omega, this is fancy notation, but all this means is that I take omega, evaluate it at a point phi of x, and plug in the tangent vector. Yeah, it's just a kind of change of variables. That's it, right? So essentially, all I'm saying is instead of integrating, like I don't know how to integrate on my manifold, I know how to integrate the coordinates. I have coordinates for my manifold, so let's integrate in coordinates and just plug stuff in like this. Okay. Yes.
Why do we need a vector? Like, what's the vector?
The vector is the tangent vectors, right? Like whenever I integrate dx1 up to dxk. Do you agree? And so what I'm going to do is I will want to plug in x1, like e1, e2, e3 up to ek of the coordinate chart. So let me draw a picture. So I have kind of my flat coordinates sent into my manifold. Do you agree? When I want to integrate something here, I have like these curved rectangles, right? Here the rectangles are straight. Do you agree? So what I want to do is I want to kind of plug in like E1, E2 in here, compute, and then instead of taking the volume of E1, E2 in here, I want to use df, look at, okay, E1 gets sent to this curved vector. Well, not curved, but it gets rotated or something. Gets sent to this vector. E2 gets sent to this other vector, right? And I want to plug that into my differential form to know how much area this here corresponds to area over here.
Okay, so the vector is not a fixed vector, but it's like all the...
Yeah, it's not a fixed vector, no. Because the point is at the end, once I do this omega, I will get something that is of the form dx1 wedge dxk, right? And it's just that once I do d phi dot v, this will come out as like some factor. In fact, it will just be the determinant of the Jacobian matrix. Okay. So maybe this is not the most clear thing yet, but the point is there's a way, a sense in which I can define integrating differential forms because they were something about volume. Okay, and I can define it on manifolds. Okay? And so here I chose a coordinate chart. This does not depend on the choice of coordinate chart. Also, okay, maybe this will only confuse you more, but here I kind of assume that the coordinate chart covers the whole manifold, which is not always the case. In that case, you'll patch it up with you'll patch up the manifold with multiple coordinate charts and then integrate in each of the patches separately and then add up the contributions to the integral. Okay, let's not worry about that. Usually you can, like for a sphere, you can give it a patch that hits everything except for one point, and that's good enough. Okay, do people kind of vaguely see the idea? I'm trying to give a qualitative picture for now, not whatever. Okay, and now, perfect. Last 5 minutes is the new part. So far, all of this has been review, mostly from last time. I promised to write suggested exercises for this last time, but I never did. Well, sucks to be you. Maybe I'll write them today. Maybe. Big if. Okay. So now, what we're going to talk about is we're going to talk about this thing called the exterior derivative. And this is very important. For many reasons, this will appear in curvature as kind of something that gives us curvature next week. And also, the exterior derivative, you may have heard of grad, div, and curl, right? It turns out that all those three things are in fact just the exterior derivative. All of them are the same thing. Grad, div, and curl, if you write it in kind of this language of differential forms, those three things are in fact the same, and they're just the exterior derivative. And I think if I write suggested exercises, I'll write suggested exercises where you can like check that yourself. It's not very difficult. But, okay, exterior derivative. How do I do this? I'll give you kind of an example, okay? So suppose we had a 2 form in R3. So I had some form which told me something about, you know, 2-dimensional like areas in R3. Okay? If it's a 2-dimensional form, then what can I do? I can look at some cube. So I can look at some point x. I can draw a cube around this point x. I'm failing to draw this point. Okay. And by the way, this is roughly like, I'm giving you like a general overview of the second half of Math 257 for you guys. So, right. So I can look at a cube. Do you agree? I have a 2 form, so let's call this cube C, and this cube depends on what? It depends on vector v1, it depends on vector v2, and it depends on vector v3, right? So I have some cube which is defined by some 3 vectors. Okay, and okay, maybe it's not a cube, maybe it's a parallelepiped, still defined by these 3 vectors. Do you agree? Okay, and I have a 2 form. If I have a 2 form and I have a cube, what can I do? I have a 2 form, I have a cube. 2 forms, what can I do with 2 forms? I can integrate them over what kind of things? Yes, over 2-dimensional surfaces. Okay. Where is there a 2-dimensional surface here? Not the just the surface of the cube. Not the I just have the surface of the cube. Okay? So what should I do to the 2 form? What should I do to the 2 form? Integrate over the surface of the cube. Very good. I can integrate over my cube my form. Do you agree? Okay. But now, hold on a second. This looks kind of interesting. So remember, this 2 form, it takes in 2 vectors as input. Do you agree? But now I'm integrating this form, and this integral really depends on the choice of the cube. Do you agree? What matters now is the choice of the cube that I choose. Right? The form is fixed, and then I can now vary a cube and get a different number. Do you agree? So hold on a second. This really is starting to look like a function that takes in 3 vectors and outputs a number. Do you agree? Pardon? Yeah, so we're arriving at Green's theorem, roughly. So this reminds you of what? So omega was a 2 form, but this is kind of maybe like a... So this is a 2 form, and this is kind of like a 3 form. But clearly it's not quite a 3 form, right? Because this form, this 2 form, it could like change quite a lot as you move out like spatially and so on and so forth. And so as I change the rectangle, it might not be linear in V1, V2, and V3, right? It might not be linear in V1, V2, and V3. Do people see why this integral might not be linear as I make the cube bigger? Yes? Because the form itself might not be constant. Okay? Good. Well, if I have something that's nonlinear, how do I make it linear? I have to look at the... Yeah, I just look at the best linear approximation. Do you agree? Very good. In fact, what I can do is I can write this out as some sort of Taylor series, roughly speaking, some sort of Taylor series. And it turns out, so this will not have a constant term. Do you agree? Why will this not have a constant term? Well, because if it had a constant term, that means that as I made the cube smaller, the integral would go down to some finite number. And I'm assuming that the form omega is smooth, and that doesn't make sense. As the cube gets smaller, the volume should go to 0. Do you agree? Similarly, this cannot have any linear terms that are strictly linear and just, this shouldn't have any terms that go like x or y or xy or yz or whatever. Why? Because if I had just x, right, then if I took y and z and kind of squished it down, I should kind of go to 0 in some sense. Okay. Essentially, sorry, I'm being very unclear. Essentially, the point is that to first order, this will have a term which we will call d omega, which will take in these 3 vectors. Okay, and then this will then have other terms of order omega v2 squared, v3 squared, so on and so forth. But the point is that if you kind of took, did this the first order is going to be approximated by some 3 form, yeah, just by some 3 form, which takes in 3 vectors, okay? And we will call this 3 form d omega. It turns out this, use equation above to essentially define d omega. Okay. Do you agree? So this gives us this operator d, which goes from k forms into k plus 1 forms. And roughly the way you get it is you look at kind of all the possible cubes that you can integrate omega on. Do you agree? And then vary the cubes. And then as a function of the sides of the cube to linear order, that will be the new differential form, d of omega. Okay? So this is not quite the way that you will see this in Moncrief or in whichever, but I think this is what Arnold does, and I think this makes the most geometric sense, because the way they do it in Moncrief is quite different. Now, roughly one way to think of this is, if omega is a flux, d omega kind of tells you the density of charge that's enclosed. It's inside the flux. So okay, we're out of time. I'll just quickly tell you the three properties, well, like a few properties of D, which kind of fully define it, and then we'll be done. So first thing that should be immediately obvious is that D is linear. Okay, right? Because doing D of omega was just doing some best linear approximation in some multilinear sense. Okay, so that's fine. The other thing is, we said that I can build every form by doing the wedge product, and we should know how it acts on wedge products. And it's just a product rule. It has a product rule, kind of like the usual derivative, but because this one's multilinear, there is a minus sign. Sorry, if people cannot see this, is that okay? This is minus 1 to the k, omega k, wedge d omega l. Okay. Right. Then decomposed with d, if you apply d twice, you get 0. These are kind of the main properties. And actually, what you can also do is you can define how d acts on a function. And one. Okay. Whoops, f. Okay. In fact, these four properties are completely equivalent to defining it this way. So defining it like this and defining it like this is the same. Why? Because you know how it acts on functions, and using this wedge thing, you know how it acts on kind of higher forms, and so you kind of define how d acts iteratively using this, using these rules. Okay. Now, I'm kind of speeding through this. I'm not quite explaining why all of this works. Like, okay, so the linear part's clear. I'm not explaining this yet. I'm not quite explaining this. There's intuitive reasons I can give for this. We're just out of time. This you can think of as it's kind of like a product rule, because this is a best linear approximation in some sense. Okay, but what's most important is we have Stokes' theorem. And the Stokes' theorem says that if I integrate on the boundary of a manifold omega, that should be the same as the integral of the manifold of d omega. But that is kind of clear. So I'll give you a moment to copy that. This is called Stokes' theorem. But this is kind of completely clear from how we defined this. Do you agree? How did we define this? We defined kind of that to linear order of integrating omega around the little cube around the point x. Do you agree? So the idea is, suppose I had my manifold M. Do you agree? I'm drawing two-dimensional case. So the boundary here is this edge. Do you agree? So I could integrate some one form around this edge. Do you agree? Yes. Now, if I did d of omega, what is that saying? D of omega is something that tells me, okay, suppose I was at a point here, and I had like a little loop around here. Do you agree? And I kind of shrunk this loop smaller and smaller to linear order of how large this rectangle is. What is the, to linear order of this rectangle? How does this like length that I integrate change, right? And to linear order, it changes like d omega. And so if I wanted to look at this big integral, what I could do is I could split it up into smaller squares. Do you agree? Okay, split it up into smaller squares and integrate around each of these squares instead. Do you agree? And I'd still get the same thing because kind of if I go this way versus this way, the common edge cancels out because I'm going in opposite directions. Okay? But this is nothing but taking d omega evaluated at this point with the size of, multiplied kind of by the size of this square, and then adding it up over all the kind of little squares. So that's just the same as saying, the integral of omega around the boundary is the same as integrating d omega on the interior. Okay, and that kind of follows from this definition. Okay, so we're way over time. I'll stop here.